Yep, we're recording. This lesson is more on indefinite integrals. So we're on page 7.
We're back to law.
Yes. This one you're not really using the log laws. It's just kind of like, you know how there's when it's I don't want to give away the joke. So this is a flashback to a joke from IB1. So antiderivatives, like integrals of e to the x and ln x. Same with the derivatives. As the derivatives of these kind of things are kind of special, the antiderivatives are special too. There's just a special thing, and they give it to you in the formula booklet. So let's revisit IB1 and one of my favourite math jokes. Sarah, can you please read out the math joke?
Why? Because you won't be able to get through it.
I gets on a bus and starts threatening everybody. I'll integrate you. I'll differentiate you. So everybody gets scared and runs away. Only one person stays. The guy comes up to him and says, "Aren't you scared? I'll integrate you. I'll differentiate you." And the other person says, "No, I'm not scared. I am E to the power of X."
What? Does anyone have want to guess?
Differentiate.
It's just
That's a good.
yeah.
That is a good. Yeah. Well, you between all three of you, you've answered it. So
You can integrate, but it's just gonna be the same thing.
yeah. When you differentiate e to the x, you get
E to the
e to the
X.
x. And so I guess similarly, when you integrate e to the x, what do you think you get? Plus
C.
Who?
That's it. Yeah, good. So what is the meaning behind this joke?
Why
So
do you
the-
have it in Z?
Because you're integrating, and integration you add is
I guess pretty good. You don't know any of this.
Oh, it's being recorded. It's being recorded.
I started watching it.
So just a reminder, this is the bit from IB1. The derivative e to the x is just e to the x. So this one was from IB1. That was in our IB1 notes, actually. That's it. Similarly,
I can see this now. I thought it was after recess.
9:20.
Yeah. Recess is 9:03.
okay, it's fine, Sarah. We're recording. You go off with your IBC. Don't front.
She's so crying.
Sarah's just gone off to
That would have just thrown off everything.
So, and as you guys said, so that bit in green was from IB1. The derivative of e to the x is just e to the x. And the antiderivative, or the integral, the antiderivative, which means the integral of e to the x is e to the x plus, remember it's uppercase C. So this is it. There you go. So that's what we were trying to write down. So this here is meant to be a bracket, looks like a written C. Okay, so the main thing of that joke is the derivative of e to the x is just e to the x. So if someone goes and threatens e to the x that they'll differentiate them, there's no threat because they just stay as they are, they don't change.
Why are they so afraid of change?
Who wants to be transformed into like some other being? You never know what it's going to be like, unless you know it's going to be awesome. So the antiderivative, or the integral of e to the x, is just e to the x plus big C. I don't know what I'm saying. That's it, e to the x plus c. So the plus c, by the way, is Calvina, you want to watch the video. So now just ask people here and there, what's c? It just means a constant term. Okay. Constant term. When we do a few more examples, you might see that. So that's what the main thing is for you to remember. By the same token, I just found this weird diagram, and this was also in IB1. By the same token, what do you think the below diagram tells you about the integral of 1 over x? I, by accident, have written ln x, but it's 1 over x. What would be, so the derivative of ln x, you guys from IB1 realize that is 1 over x. So that's a flashback to IB1. Anyone want to guess what therefore the integral of 1 to the x will be? Yeah, ln x plus c. That's it. So So the main thing to get from this, so as you're going from here to here, you're integrating. Integrate. This one is integration. If you're going the other way, you would be doing differentiating. Going this way is differentiation. Differentiation. So going that way is differentiating, going this way is integrating. Because it's integrating. Integrating. But there would be a plus C here. And as you said, ln x plus c. When you're integrating, there could have been a constant. So that's a wacky diagram where if I just look at that, I'd go, what? So, well, let's write a sentence. So the integral of 1 over x is ln x, as Bella said, plus c. This thing is in the formula booklet. So they remind you that the integral of e to the x is e to the x plus c, and in the formula booklet they remind you that the integral of 1 over x is ln x plus c. They also happen to say on the side, on the formula booklet, there was a little side note, that, what does that mean in green? What does that actually mean literally? X is greater than 0, yeah. Okay, so why, if you try to take, just out of interest, ln of a negative number, like -2, why is that not possible? Like if you plot that in a calculator, you'll get an error. Because ln, remember, is log e. Yeah, why, what is the, when you do logs, what's the answer meant to be? It's a power. Yeah, it's a power. Because e to the power of what equals -2?
Nothing.
Yeah, exactly. You can raise e to the power of anything, like -5, you'll just get like a small number. You get closer and closer to 0, you don't actually get below 0. So if you raise anything to the power of something, you'll never get a negative number if e was positive, kind of thing. Like, but whereas if you did like something like -3 cubed, you get -27. But assuming e is positive, it's not a negative e we're raising to a power, it's e. We don't have the negative base. So it's all because, and can e to the power of anything equal 0?
1.
Yeah. E to the 0 equals 1, yep. But e to the -1,000,000, does that ever equal 0?
It gets closer and closer, but never reaches it.
Exactly, it gets closer and closer.
How
It'll
do
be
you
like
know that?
1 e to the, the negative exponent law. Remember e to the power of a negative? You write it as 1 over e to the power of the positive. And that's just a really big number now in the denominator. So 1 divided by a massive number just is getting closer and closer to 0. So as you divide by a bigger one by a bigger and bigger number, you just get closer to 0. You never hit it across it. So that's why on the side, in the little formula booklet, they've got this little definition. So occasionally in our answers, if it's something where we're changing 1 over x to ln x plus c, we might need to state something like this green thing on the side. So that's something that I sometimes forget to do myself. That's when the answer has got a log in it. So for x value is greater than 0, because the x can only be a positive, because e to the power of anything will only ever give you a positive number. So that's why on the side in green they've got x to the 0. So we should probably make a note of that, shouldn't we?
Yeah.
So as you could say ln 0 is undefined, or that's ln of 0, ln of a negative number, undefined. If you've got the time, you might want to write y, e.g. e to the power of something will never give you 0, or e to the power of a number, negative number will never, no, e to the power of anything will never give you a negative. So that says, by the way, as ln of 0 is undefined and ln of a negative number is undefined. So a little note on that might be something worth popping in. I find it easy to forget when I'm writing an answer that's got its ln in it for integration. I might forget to put a little side note on green. So that diagram also from IB1 was also the derivative of ln x is therefore 1 over x. That's from IB1. So let's just pop that in. Ln x is 1 over x. And this little bit here, just a little flashback from IB1. That's what this thing is. So the main new thing is the stuff on the right, and on the left was just a little flashback. Because you'd probably notice a lot of, in exam questions, a lot of integration problems maybe also have a bit of differentiating involved. So it's good to practice some regular calculus from last year as well. So a few people just writing some stuff down. Getting on deep, isn't it? Okay, so we'll probably just get through the next page today. That's fine. Because this is meant to be over 2 lessons, this one. Can I go to the next page? Coolio. Okay, here's some little examples. Find the indefinite integral of the following. So, Kavina, this little weird symbol we call the twig. We just made up the name. Let's make up a name for it, the twig. That little symbol, yeah, it means integrate. Yeah, it means do the reverse of, remember when we did calculus, we differentiated? It's more like if you had the answer, how would you go back to the original, what it was originally. So it's the reverse step. So
I talked about this in physics.
Oh, do you? Okay, that's good. Oh, that's, like you'd be happy that you're finally learning it now too. You probably wish we taught it in 91. So yeah, that's what the universal symbol is, the twig integrate. So for e to the x dx. Oh my god. All right, cool. Oh yeah, because it's e to the x stuff. So notice all the going on. So this is because it's an e to the x thing. That's a 1 over x thing, and that's an e to the x thing. So this is just practicing those kind of things. The fact what we did on the previous page. So there's a bit of a funny way you can set it up. Notice 4 is just a constant term. So 4 is just a number multiplied by e to the x. So you're allowed to rewrite the question with 4 out the front. Take the little constant out. Draw our twig, and then just e to the x. The dx just means with respect to x. That's what it means. So the dx isn't part of the function. It just means it goes with the twig. The twig and the dx go together. So it says integrated with respect to x. So this one is saying integrated with respect to t. That's all it is. That's the t and the dx thing. So our function, all we've got to do now is integrate e to the x to start with. So what is the integral of e to the x? Yes, it is. Perfect. And plus? Oh, just it's even easier than that. Plus the constant, yeah. So that's all it is. So the integral of 4e to the x is just 4e to the x plus c. But sometimes, like, taking a little constant out the front here, like I did in green step, wasn't super necessary in this one. But there will be some problems later in this unit where it makes life easy if you take that thing out and then pop it back in later. So just showing that that's a possibility. So some of you might have gone straight to realizing, okay, that's not a composite function at all. It's just a function times by a constant. It's not like it's x e to the x or anything like that fancy. It's just a normal thing. So yeah, you could have gone straight from the blue question to the answer. But this little thing is a possibility, and that's a handy step in some later, more complicated questions. So that's why I thought I'd just point it out now that you can do that. So that's lovely.
Wait, what did you say?
The fact you're allowed to take a constant out the front. If it's just a regular function times by a constant,
Yeah.
you can pop the little constant out the front and then pop it back in later.
Okay.
But notice that it becomes 4e to the x. It doesn't become 4e to the x plus 4c, because c is just a constant. It doesn't matter if it's a multiple of 4 or anything. Just leave it as 4e to the x plus c, an unknown constant right now. We can do a similar thing. I'm going to do a similar green step. So would you agree that this original function, it's like 1 over x? And that's the one that we know turns into ln x plus c. So what's a constant that I can pop out the front? 3, yeah. Because that's like 3 times 1 over x, isn't it? So if you want to make a note of it, you can think of it as like 3 times 1 over x, in case you want to realize why we're taking 3 out. So we can sit by a similar note, take 3 out as a constant, and then it's 3 times the integral of 1 over x with respect to x. And what is the integral of 1 over x? Again? Ln x. Yeah. So we can write our answer as 3 ln x. Yes, that's right, 3 ln x plus c. Easy to get that plus c out of quite a bit. And with these ones, remember when it's got an ln answer to an integral, we've got to also do that funny thing in green on the side that they do in the formula booklet. What values of x? X can't be
It has to be greater than 0.
greater than 0, yes. So it's just ln x. If it was ln in brackets, if it was something like ln brackets x minus 2, then it would be something different, like the x is greater than 2. Because 2 minus 2 would make that 0, yeah. So it can vary, but because it's just ln x, it's just x is greater than 0. Let's pop that in as well. So they like you to state that in your answer. Which values is x defined for in the natural world. And if you forget, like just look in the formula booklet because they put it next to it on the formula booklet, so that jogs your memory a bit. So having formula booklets open can be handy for jogging. Okay, cool. So that next one is e to the t with respect to t. Just think of it as like e to the x dx. But has e to the x, e to the t has been multiplied by a constant? Like it has been divided by 5. But when we're thinking what constant would go out the front, we think what would be multiplied by instead. And yeah, it's a fraction. 1 over 5, yeah. So think of it, even though it's divided by 5, what needs to go out the front is you're going to put this constant at the front. It's, yeah, what you multiply it by. Yeah. 1 over 5, draw your little twig. E to the t. T. Yeah, I know. Pretty much almost every other one I've got has x in it. I understand what you think that. And then how would we write our final answer?
1 over 5.
Yeah.
E to the t plus c.
Yeah. E to the t plus c.
Just maybe e to the 5.
Yeah, totally. That's okay too. So let's maybe write that. Or 150 to the t plus c. Or e to the t over 5 plus c. This is regular stuff, like regular rules. That's good. Because sometimes it does me too.
Sometimes.
What did you say? There's something about it, like, you know, it just defrags the brain. Like when I had a little break from, like, you know, I studied and did other stuff first and then became a teacher, and then when I started doing maths again, like regular maths, on a regular basis, it's like my brain started working better and function better or something. I think it just defrags the brain, but probably that's if you like maths. If you don't like maths, it might not make you feel better. You don't get a pass from it. Must be activating a certain part in your brain or something. Yeah, it could be, yeah.
Do you feel better to answer jobs?
I like algebra for some reason.
I like algebra because I love algebra help you like do a certain job better. Is that what you mean by defrag the brain?
Oh, defrag the brain. Yeah, make me think through things clearer, and like can make you feel a little bit of a happy buzz.
Yeah.
Yeah, it can be a bit of a happy buzz. There's something satisfying about it too.
I like the way like you figure it out it's on the line and like you're very organized. Yeah, that's not me. That's not me.
That could be fun.
Okay,
Like a flow of thought process kind of
I'd
thing.
be like, fine, I need to do something right over here and I'm doing my first. I'm like, okay.
I don't know why, but physics, I worked right to left, a little left to right.
Yeah, I noticed that. I remember we were working together on that.
Yeah, I worked left to
And I
right.
was like, she's good.
Oh, good. We've got time to do this. It's nice. So these ones are a little bit longer. They're giving you a little bit more space. Find the indefinite integrals of the following. So these aren't related as much to the ln e to the x one. It's just examples of slightly more complicated ones in terms of algebra. So 2x minus 3 squared is a composite function. So there's a way that you'll learn later where you could do this. It's almost like a chain rule, but for composite, for integration. But 2x minus 3 squared is super easy to expand, isn't it? And just turn into a regular function. Yeah, so when it's something simple like 2x minus 3 squared, you probably want to expand it. Whereas if it was, instead of squared, it was to the power of 5 or something, you probably don't want to bother expanding it. Unless you had loads of time to check an answer and you wanted to use binomial theorem and expand it. But like, so when you get equals to the power of 5, we'd use another technique which you'll learn next lesson. But if it's something simple like this squared, then yeah, let's expand it first. So let's expand the original function first. I'll write it in blue. 2x, well, by this, what am I talking about? 2x minus 3, 2x minus 3, all the FOILing stuff. Expand first is easier for this one, because it's just a square, it's just a quadratic. So when you expand that, I think you guys were starting to say what it was, it was 4 something. 4x squared. Yeah, what would the two like terms combined be? I just don't have much space, so I'm not going to.
Negative 12. I mean, negative 12x.
Yeah, negative 12x, yeah.
9.
Plus 9, yeah. And so that's in. And then, so I'm rewriting the original question, and I'm going to put the twig. Let's put the twig there. I'll do it in green so you can sort of see. There's my twig and the x, just so you can see it's different colour. So I've rewritten the function and put a little twig to say integrate that with respect to x. Sometimes they put a bracket around it if it's kind of a few terms together. Sometimes they don't. I just thought I will this time, because otherwise it looks a bit confusing. So then then that's not too bad. Then we just separately integrate each little one and throw a little plus c at the end. So this is not too bad. Now we can go straight to the answer. 4x squared. What would be the new exponent?
3.
Yep. So you rewrite it 4x cubed over
3.
yeah, over the new exponent. Yeah. So that's how you integrate polynomials. Because if you did this, if you do the reverse, differentiate that, you'll get 12x squared over 3, and 12x squared over 3 just becomes 4x squared. So see, we increase the power by 1, keep the coefficient, and divide by the new power.
Why?
And then simplify. Because you have to divide by the new power, because if we didn't, go back. How do I do that? Doesn't matter. So if we didn't, we would just get 12x squared. See, my notes are important. My little notes are important. Or else Katie would be wandering the streets. And then you'll find us again. You'd go sort of searching for us. But she might be my friend. You probably didn't even see it. Here I am boasting about my notes. Yeah. Hey Katie, how did you know we were here?
So Sarah was right there.
I think Sarah was wrong. Wait, what happened, Sarah? Sarah was saying that don't write the note because they're not going to come back on it. Oh, yeah.
I was wondering if Katie just find us just like random wandering anyway.
No, I'm wondering.
I still don't know why you did that.
Oh, Katie, so I've given you a new 7 and 8. You hadn't written all the old 7 and 8. There was just one boo-boo on it, so I thought rather than correct it, I'll just print it again. So feel free to throw away the old 7 and 8, and you've got the new 7 and 8. Page 7 and 8. I'd given you 7 and 8 before, but we hadn't written on it yet. And there was just a tiny boo-boo on it, so I thought I'd just give you the new one. Okay, so, oh, sorry, yeah, Gary was explaining it to me.
Miss Maloney, can you scroll up really quick?
Yeah, sure.
Second copy, Krista.
Okay, Kia, that might be better, because then you can see the first page.
Because you have to. Miss Maloney, write it out. Think how it's not on
No, I'm like that too. I like to write out every step.
As in, like, what I did, what you do?
Why did you do that? And Miss Melanie skips a lot of stuff to make sure.
She said, how do you get 12?
How do I get 12?
Yeah.
Where?
Let's write a multiplication sign between 4 and 3.
Yes, she said it equals 12.
What equals
No, 4 times 3.
What? 4 times 4 is 12.
It's 24. It's 20.
Why don't you talk?
Well, see, this is why I was name was just explaining to me and saying all this stuff.
Yeah, because 4 times 3 is 12, so if you
Why did you multiply 4 and 3?
That's what we never did calculate, right? Yeah. So if I asked you to find dy
What? That becomes 12x squared.
Yeah.
Okay, yeah.
They talk about it. Yeah, I told you.
It's
So,
12x squared.
so when you integrate something, you can check the answer by doing the dy dx of it. And
We're not
see if
gonna
it
have-
goes
I got you.
Yeah. So that's why you can check if you're in doubt, like, hey, have I done this right? And then, minus 12x, what would be the new exponent?
1 and 12.
It would be 0.
1.
Yeah, because before it was 1, so now it'll be 2. And then you always divide,
Why is it 2?
because a square will differentiate to become an x. Like a cube differentiates to become a square, then differentiates to become an x. And then you always divide by the new exponent. And then you simplify. So, hey,
Why? I would add 0x squared.
yeah, because otherwise, if you can divide 12x squared by 2, you get 24x. And we need to get 12x. And then with this one, if I can divide that 4x cubed by 3, I would get 12x squared. And we need to
Yeah.
so someone's investigated, some math person investigated this and realized it was raise the power and divide by 2. And then simplify it.
No, you might.
Okay, so what kind of term would give us plus 9?
9x.
9x, yeah. So would you agree, like if you differentiated 9x? Yeah, plus C. Easy to forget plus C. Let's choose.
I copied about
So this is pretty good, but it turns out I can simplify one of the terms.
Yes. You could simplify 12 and 2.
Yeah, 12x over 2. So just showing you sometimes in the book, you can leave the first term as 4x cubed over 3, that's fine. But sometimes in the book they'll have written their answers like,
Wait, how did you get 9x?
Because
9x. When you,
Bad.
oh, yeah. Thinking back to calculus from IB1, when you differentiate 9x, you get 9. Because that's like 9x to the 1. So 9x to the 0. Okay, so, and then minus 6x squared plus 9x plus c. Now, as I said, you could have left the first term as 4x cubed over 3, but just being aware that you could also write it as 4 over 3x cubed. In our textbook, they tend to turn the coefficient to a little fraction at the front. So in our textbook, they tend to write something like that, more like this, but both are fine. Both are okay. Just so be more aware that that is the same thing as that. Yeah. So you wouldn't get confused and think you had it wrong. That was fun. Whereas this next one, remember you can break up a numerator? You can't break up a denominator, but you can break up a numerator.
You do x on the bracket.
Yeah, we're going to rewrite the thing.
Oh, 1 over x?
Yeah, there's going to be an x squared over x minus 2x over x plus 1 over x. And the 1 over x is going to become ln x when you integrate it.
But I mean, couldn't you just take out 1 over x and put it before the little twig? That's what I would have done.
Oh, that would be, outside the twig has to be like a number, like 1/3 or 5 or something like that. Yeah, I get that. That's a good question. Yeah, no, keep the x on the end.
Why?
Because we want to integrate with respect to x. But if it was a constant term, if there was a term that was in, like just a number that was in all of them, it's fine to just pop it out there. It just makes life a bit easier. If you're puzzling.
You do x squared. Oh, I mean, so much the answers.
Oh yeah, so at the moment I'm still writing in blue because I'm still just rewriting the original one.
Rewrite it to say x squared over x.
Yeah.
Minus 2x over x.
Yeah.
And then plus 1 over x.
Good, yeah.
And then do you just take out x?
Yeah, good. Then we can cancel down where possible. So x squared divided by x. So see what we did was we broke up the numerator because this is because the first two terms will simplify to something really easy to integrate. So x squared divided by x, what does that simplify to? X, yep, good. X minus 2x over x, what does that simplify?
Minus 2.
And unfortunately, 1 over x we're still left with. But we know the integral of 1 over x is? ln x, good, yep. So that's going to make life easy. And now, and then just don't forget the question was all integrate and all that kind of stuff. So I'm going to pop the twig on our nice little simplified version, pop our little twig. I might put a bracket. And then dx. just so I've got the nice notation there. Just to remind us, what is this question all about again? And then you can separately integrate each little bit. Yeah, good. So if you integrated x is like x to the 1. So as Bella said, that would be x squared now over 2 minus, what would differentiate to give you 2? Yep, 2x, yep. And according to the previous page, what's the integral of one of x? Ln x, yeah.
Just see below.
Yeah, don't forget your little plus c. Easy to forget everything. Yeah, that's good. So you could have written it like that, or fine. And according to ln x, what value of x is, what are the only values of x that are allowed? Greater than 0, yeah. So we've still got to put that on there somewhere, like write it on the side or whatever, that's way, so I'll do it down here. So here's a lovely, lovely little answer. That's just fine. And I just like to point out as well, sometimes in the book, they'll, instead of x squared over 2, they'll have written that as a half x squared. So don't be confused and think that means something different. So just be aware that that's the same. And then x is greater than 0.
Class A is from me.
Do you want to finish the last one really fast? No, that was a clear note. Yeah, we're only partway through the lesson anyway, so I'll stop it here. Gemini? Yeah, you got a little bit of IOC study, thanks to the board not working.